Okay, go ahead, please, Dalibor.
Okay, so the next talk, the first paper, is called Towards Hybrid Isolation for Shared Multicore Systems. So we will have a nice continuation, starting with the keynote. And this talk, I think, will be delivered by Yoonsung Nam. Uh, and in this talk, our colleagues from Korea will discuss the problem of resource contention amongst well-collocated tasks in multi-core systems, and they will illustrate some trade-offs between software and hardware isolation techniques. So, if Yonsung is with
Young
us,
is here.
Hello, I'm here.
hello.
And
Nice to
thanks
see
so
you.
much
Nice to meet you.
for staying so late, Youngsung. We really appreciate finding a time that works for everybody from California to Korea was
Yeah. Okay. Let me start my presentation.
Yes.
Sorry.
If you want to share the screen, you have to close the chat part of the screen, because with
Okay.
the chat open, you won't see the bottom part of the one that allows you to control the, yeah. So just close the chat and then go to the right bottom of the screen, and you should see a button to share a screen.
Okay. Can you see my slides?
Yes?
Yeah.
Perfect. The floor is yours.
Okay. Hello, I'm Yoonsung. I'm a PhD student in Seoul National University, South Korea. Our paper name is Towards Hybrid Isolation for Shared Multicore Systems. And this work is about optimizing isolation techniques to mitigate performance interference caused by resource contention. In these days, in data center, from data analytics to machine learning program, many workloads are running on the server machine. These workloads can be divided into two groups based on their service level objectives, called SLOs, latency critical one and best effort one. So co-locating these workloads on a server machine gives some benefits in terms of high resource efficiency, and it also enables running multiple workloads in parallel. However, once collocating workloads in a machine, it may cause resource contention. As illustrated in the figure, there are several shared resources such as last level cache and memory bandwidth, and contention on these shared resources makes lower performance, a lower resource efficiency, and higher service objective violations. To handle the resource condition, there are some isolation techniques in multi-core systems, software one and hardware ones. First, software isolation techniques are usually implemented and performed by software. Linux SIGRIP is one of the representative isolation techniques in Linux, and Using C groups, we can allocate CPU cores through the CPU cycles and perform thread migration. Second, hardware isolation techniques are provided by many hardware vendors, such as Intel and AMD. For example, Intel provides hardware cache partitioning called Intel cache allocation technology. These two types of isolation techniques have been used to mitigate resource contention, and there were some software-only approaches. They only use the software-based isolation techniques, which does not require hardware features. CPI2 and memguard and QSA are those approaches. And on the other hand, there are hardware-only approaches such as Dirigent. And lastly, Heracles and Partis used both isolation techniques. However, there is no study on these multiple isolation techniques, such as characteristics or which isolation technique is better. And here we have studied how software and hardware isolation techniques are different. How can we use isolation techniques properly according to characteristic of workloads? Actually, isolation techniques can be characterized by the strictness, responsiveness, and flexibility. Generally, hardware isolation techniques are fast and strict because they directly control hardware or segregate resources. And software isolation techniques are usually slower than hardware ones. However, they are more flexible. Here, flexibility means how many options are available for isolation. For example, CPU cycle limit can handle resource contention at 1% granularity, but per core DBFS only have 10 frequency per CPU core. Thread migration has only 2 configurations, but moving threads to other socket can effectively reduce severe contention in a socket. Using some isolation techniques, we conducted some experiments. We co-located stream cluster and canal as the foreground and use SP, which is high memory intensive one, as background one. And we ran them on a 16-core socket. We statically used multiple isolation techniques to show which combination is the best one. In this experiment, we used hardware cache partitioning, per-core DBFS, and CPU allocation. Yellow stars in the graph shows combination of the highest performance. Canyon shows in the right graph reach to the highest performance when using all isolation techniques, but stream cluster shown in the left graph achieves the highest performance when without using partitioning approach. And red stars show the case of performance degradation when using hardware cache partitioning. Here, stream cluster does not benefit from it. It's because the stream cluster has very low last level cache hit ratio. Firstly, to analyze the trade-off in terms of strictness, we compare hardware cache partitioning and CPU cycle throttling. As shown in here, obviously hardware partitioning can segregate cache resources strictly. However, CPU cycle limit cannot isolate cache resources, and the cache size are shift over time. This explains why hardware isolation techniques give more predictable performance when isolation, as shown in the bottom graphs. And secondly, to show different responsiveness, we collocated web server and memory-intensive workload and generates high load to the server. And how hardware and software isolation techniques quickly throttles co-located SP workloads. Here we compare CPU cycle limit and per-core DBFS. As shown in the graph, per-core DBFS achieves lower tail latency due to the hardware isolation techniques, low overhead. Lastly, we studied flexibility of isolation techniques. We placed 4 workloads as shown in the figure and perform isolation using hardware cache partitioning and thread migration. The graph shows that aggregate performance is improved by 20% when using thread migration, which swaps background workloads to mitigate contention in a socket. Hardware cache partitioning cannot perform this type of isolation because it only works for an LLC. Here's the design of our prototype, HIS, is a hybrid isolation system. With these observations, we implement our system. It consists of profiler and scheduler. The profiler periodically monitor performance counters of foreground workload and profile resource contention and sends contention information to the scheduler. Then scheduler chooses an isolation technique based on the information, available techniques, and the types of isolation technique. Our online profiler measures how much workloads suffer from resource contentions. This can be done by calculating contention using samples when the workload runs alone and co-run with collocate other workloads. To do this, the profiler collects samples of performance counters when the foreground workload run with other workload. It checks any valid contention information first, and if there is no valid profile for the foreground workload, then initiating profiling mode. Here, profiling mode means the profiling the Solar sample data for the foreground workload. It utilizes signals such as sigstop and sigcount and use sigstop to pause background one. Then the profiler can collect the Solar samples of foreground workloads during predefined seconds. And after collecting samples, at the time, it resumes background one and starts to collect co-run samples. In this way, we can measure resource contention for each resource type. With this profile data, the scheduler can perform isolations. Firstly, it checks which is the most contentious resources and checks if there are corresponding isolation techniques. Among the isolation techniques, the scheduler chooses hardware isolation techniques if it is available. Once the isolation technique has chosen, it searches for isolation parameter. If resource contention is severe, then scheduler decides to strengthen the isolation for the foreground one. After performing isolation, the scheduler sleeps for predefined interval. Here, we sleep the scheduler for 200 milliseconds and get feedback from profiler. If still the contention is high, then the scheduler iterates iterate from step 1 to step 6. Otherwise, the contentions are well managed within the threshold, then scheduler stop to perform isolation. We conducted some experiments to test our prototype on 16-core multicore socket. We compared ours with static isolation approach. We tested 2 types of multi-threaded workload benchmarks, and one is batch workload, and the other one is latency critical one. We used the background SP of NPB workload as a background workload because SP shows the highest memory bandwidth and LLC usage. First, we collocate 2 batch workloads on a server. X-axis shows foreground workloads, and SP is collocated as background one. Y-axis shows performance normalized to the baseline, which corresponds with static CPU isolation. In this evaluation, our system achieves up to 1.7 times than better performance than a baseline. We also conducted experiments for the latency critical workload and Apache web server here. We used client sends request generated with Pareto distribution to the web server. As shown in the figure, his achieves around 2 times lower latency than baseline, and also show slightly lower latency than Solarone case, 8-core Solarone case, thanks to the CPU allocation techniques, which allocates more cores responding to foreground's CPU demands. As future work, we will test our scheduler using other isolation policies, and we will conduct more experiments with more diverse benchmarks, such as phase-changing workloads, and we will compare our work with recent works, such as Hercules-like system, which uses both hardware isolation and software isolation techniques. In this work, we have analyzed the trade-off in hardware and software isolation techniques, and also implemented a prototype for a hybrid isolation system. We have evaluated our prototype using selected benchmarks and achieved around 2 times performance improvement than static isolation. And thank you. And thank you for listening my presentation. And have any questions?
Yeah, thank you very much. Thank you for keeping the time. Are there some questions? I will check the chat. If not so far, maybe I missed that, but I would like to know, in your solution, how do you choose whether to use software or hardware contention avoidance technique? What is the logic behind the selection between these 2 approaches?
Actually, our prototype favors hardware isolation techniques over software isolation techniques because it provides more strict and responsiveness. But the problem of hardware isolation technique is they have limited configuration. So once they used all configuration search for the hardware isolation, which means, in other words, if the contention cannot be managed with the hardware isolation techniques, then software isolation techniques can give more option for to mitigate resource contention. Yeah.
Okay, we have another question. Thank you. We have another question from Agung. Would you like to say it yourself?
Okay. Hi, I have a question. Thank you for the great talk. If I understand correctly, you consider the contention independently for its resource, right?
Yeah.
So in some cases, reducing the contention of one resource can increase the contention of other resources.
Yeah. Yes.
Do you investigate or consider those cases?
Our scheduler deal with the situation, so there can occur some ping pong situation. Some contention may be solved, but another contentions occur. But in the case, our scheduler decided to mitigate the most contentious one. And if the ping pong situation occurs continuously, then the scheduler we can set the threshold to avoid that oscillation effect.
Okay, thank you.
Okay.
Okay. Thank you once again. We will move to another talk. So I would like to invite Megana to tell us something about her work